Welcome to solverfy.
Okay, so you need to compare the conjugate base of an alkyne, an alkene, and I guess I can be consistent and put a C here as well. That helps. Okay, and an alkane. And I think you have the correct answer. The conjugate base of the methyl or the methyl anion is indeed the correct answer. If you want to talk about why that is, which is what I'm guessing you're looking for, given that you have the correct answer indicated, the best way to think about this is to consider if these are the conjugate bases of their respective acid, what do the acids look like? Right, so in the case of the alkyne, right, that's just going to be your typical alkyne like this. And for your alkene, it's going to look like this. Right, and for your alkane. And if you remember that if you have, I'll just write acids here. The reason this helps is because the strength of a conjugate base is inversely proportional to the strength of the acid. So, say 1 over proportionality constant, acid strength. What that means is if the acid is strong, the conjugate base is weak. If the acid is very weak, the conjugate base is strong. So whichever of these is going to be the weakest acid is going to be the strongest conjugate base. Or you could say whichever of these protons is hardest to pull off is going to provide us with the strongest conjugate base. So another way of restating what you cited, that the methyl anion is the strongest conjugate base, is saying that it's harder to pull a proton off of an alkane than it is to pull a proton off of an alkene or an alkyne. And if we look at the pKa's, or the relative strengths of these acids, right, an alkyne is somewhere around 25, an alkene is somewhere around 43, and an alkane is somewhere around 50. Now, what that means is that if we want to compare an alkyne to an alkene, see there's a difference of 18 here. That means it's 10 to the 18 times harder to pull a proton off of an alkene than it is to pull off an alkyne. Then there's a difference of 7 here, which means it's 10 to the 7 times harder to pull a proton off of an alkane than it is to pull one off of an alkene. Okay? And that's effectively what we're measuring with acid strength, is how hard is it to yank this proton off. Right? So 25 is doable in a lab setting. You can deprotonate an alkyne, with chemicals and room temperature. You get into alkene and alkane, it gets much, much harder. Right? And the hardest of them all would be the methyl cation. If you want to talk about why that is, one final level of sort of abstraction here, and has to do with the fact that alkynes, this carbon is sp hybridized, and an alkene, this carbon is sp2 hybridized, and in an alkane, this carbon is sp3 hybridized. Okay, then remember that when you're pulling off this proton, you're just pulling off a positive charge and leaving behind a negative charge. So the process of this behaving like an acid is losing H plus, right? So kind of a way that you can think about this is that s orbitals, right, are more positive or closer to the nucleus than p orbitals. Okay, so s closer to positive nucleus than p. Oops, not than plus, than p. Okay, so an sp orbital is kind of more positive, and then an sp3, because it's made up of one s orbital and three p orbitals, is less positive of an orbital. So, and then alkenes are between the two. So the question is it easier to lose a positive proton, a positive hydrogen, from something that's more positive or from something that's less positive? Easier to lose H plus from more positive sp orbital than sp2, sp3. It's like saying it's easier to remove positive things from things that are more positive, and that's because, you know, two things that are positive repel each other. Things that are negative and positive attract each other, and two things that are negative repel each other. So at the heart of it, it has to do with the shape of these orbitals and how close they are to the nucleus, and therefore how positive the orbitals are. That's still just a simplification, but if you wanted to know why that was the case, that's why.